Yeah, hello, welcome to today's lecture. So we are in our lecture notes and we move now to chapter 2 about Hilbert's 17th problem. So David Hilbert gave a list of 23 problems which he presented at the International Congress of Mathematicians in Paris in the year 1900. And yeah, about more or less, I guess, 10 problems have been undoubtedly solved. And one of these is Hilbert's 17th problem, which was solved in 1927 by Emil Artin, an Austrian mathematician. So in order to solve this, Artin had to develop together with Schreier the theory of ordered fields and also the notion of real closed fields. So we will actually present the solution to Artin's solution to Hilbert's 17th problem in subsection 2.5. And it will be quite easy for us to solve it because we have such strong tools as real quantifier elimination. I mean, Artin had only slightly weaker tools, but this was enough to solve it. So what is Hilbert's 17th problem? Well, the problem is that if you have a polynomial over the reals, or at least you can state it in this way. Hilbert stated it technically slightly different, but it amounts to the same thing. So if you have a polynomial over the reals, and you know that f is non-negative on the whole of Rn, that means in every point of R to the n, this polynomial takes a non-negative value, then we will actually see that f is not necessarily a sum of squares of polynomials. If it were, then this would be a very nice certificate for f being non-negative, right? Because sums of squares of polynomials are, of course, always globally non-negative in this sense, because sums of squares of real numbers are non-negative. So Hilbert already knew that such a non-negative polynomial is not always a sum of squares of polynomials, but he asked whether it would always be a sum of squares of rational functions. And that turned out to be true, right? So Artin proved that f is a sum of squares of rational functions. That turned out to be true, and in order to prove this, we will need many ingredients from our first chapter. But it will be then quite easy actually, up to these difficult ingredients. So now to prepare a little bit, because it's not very well motivated to prove Artin's solution of Hilbert's 17th problem, we will see a bit what is the situation for polynomials in one variable, what is the situation for polynomials, for quadratic polynomials, that means polynomials of degree at most 2 in several variables, and we will also see that a non-negative polynomial in several variables is not always a sum of squares of polynomials. So more precisely, we will learn about a tool that's called the Newton polytope that can help in proving such statements. Yeah, and so now we go to the first subsection here, namely non-negative polynomials in one variable. So non-negative polynomials in one variable. So suppose R is a real closed field and F is a polynomial. So we are doing everything already over ordered fields or real closed fields as far as possible, of course, right? So R is a real, but it's also already interesting if R is a field of real numbers. Suppose R is a real closed field and F is a polynomial in one variable, capital X over R, a univariate polynomial. When the following are equivalent, so F is non-negative on R, so meaning that F is, if you evaluate it in any element from R, you plug in an element from R for the variable, then you get a non-negative element in this real closed field. Right, so, and second, F is a sum of two squares of polynomials over the same real closed field. And third, F is a sum of squares, of any number of squares, right? So this refers just to this notation, I guess, and this refers to this notion of being non-negative on a set, right? Okay, so from B to C is trivial, of course. From B to C is trivial. From C to A is also trivial, of course, right? So in order to show that, so it remains to show that A implies B. So in order to show this, we adjoin a square root of -1, not to a real number, sorry, but more general here to a real closed field. I have to correct this in the lecture notes. We adjoin a square root of -1 and consider the following ring orthomorphism on this polynomial ring in one variable over this extension field C. Namely P maps, so we will denote it by star, so P maps to P star, that's the notation for the thing we will define. And that's given by, that's like complex conjugation, right? So that's, for polynomials, by conjugating the coefficients, like it's like complex conjugating the coefficients of a polynomial. So on the elements of a real closed field, this should do nothing. When I extend it, to C by saying that I star should be -I. So that's that you can do by algebra, right? Because you know there is an R automorphism of C mapping I to -I since x squared, since I and -I are roots of irreducible polynomial x squared plus 1. Right, and this is the splitting field of this polynomial. So that's a field which you get by adjoining the roots of this irreducible polynomial. So in one way or the other, you have certainly seen that in your algebra course, in the field theory course, but of course you can just prove it again. There is only one choice. You know how it looks like, because the elements of C are all of the form A plus a plus ib with a and b in R. So you know what this automorphism must do in a general element, and then you can of course define it in this way and calculate that it's an orthomorphism. But you should really know this from field theory. So, and that's exactly like complex conjugation, of course. And then, so I have now this automorphism on C, from C to C, that maps A to A for A in R, and I to minus I. And I can extend this to a polynomial ring, you know, because I can define a kind of evaluation homomorphism, saying that the coefficients are mapped with this automorphism, with this homomorphism, ring homomorphism. Doesn't matter now that it's an orthomorphism. And x I can send to anything I want, and I send it to x again, right? And so you see that that I get this. So of course you can do it also. You can do it also. You can prove it also in an ad hoc manner, right? So without loss of generality, f is not a zero polynomial, because when I want to show that f is a sum of I want to show that a implies b, so certainly the zero polynomial is the sum of two squares, right? 0 squared plus 0 squared. And by the fundamental theorem of algebra 1.4.14, of course that version for real closed fields, let's look at it again. I can factor, I know that the irreducible polynomials are the irreducible monic polynomials in R adjoint X are of a form x minus a, where a is in R, and when we have these certain quadratic polynomials, x minus a squared plus b squared, where b is non-zero, right? Of course, you see that these don't have a zero in R, whereas these obviously have one, right? Okay, so and I use that, so I write f as a product of irreducible polynomials. That's possible. I'm in a factorial ring. So, and then I know how these look like. So by the fundamental theorem of algebra, there exists, okay, let me first write it. So I can write it like, you know, f mustn't be, f is not necessarily monic, so I can take its leading coefficient c, that's a non-zero element from the field R, and then I have a couple of quadratic factors of this special kind, so the bi's are non-zero, and then linear factors. And for the linear ones, I assume that the dj are pairwise different, right? So I can assume this if I introduce here some exponents alpha j, some positive integers, to compensate for the multiplicities. Yes, and otherwise, I mean, the ai and bi might appear several times. Here I don't have exponents. Okay. And now, the basic idea is to split these things up. So first of all, this part, the basic idea is that I split that up. So I pack all the, I pack half of these. So yeah, you can always, you can always factor this further, right? So such over C you can factor it, right? So because x minus a squared plus b squared is, of course, x minus a plus bi. times x minus a minus bi. Yeah, so namely if you, we have seen that already anyway, but if you multiply this, you get x squared. When you get here a plus bi times a minus bi, but that's a squared plus b squared. And when we need here still the mixed term here, that's 2 minus 2a minus 2xa, and but that's exactly the same as this times this, so x times minus a minus bi, and then x plus x times minus a plus bi. Okay, so that's you know, and so over C I can write these, I can factor further this quadratic polynomial into these two linear terms. And now I pack one of these linear terms, one of the two linear terms I pack into one polynomial, and the other I pack into the other polynomial, right? And now suppose now that that f is non-negative on R, when I know that okay, for each x in R, we have that the signum of f of the sine of f of x is greater than or equal 0. But that's the sine of C times the product of the sines of the x minus dj to the alpha I, because the sine is multiplicative, right? And this here is or take this here, that's always positive, right? So from this we deduce that so here I only use this equation here. I don't use that one already. So I don't use that one yet. So from this we deduce easily that each alpha I must be an even number. Why is this? Okay, so because look at the dj's. The dj's are pairwise different, right? So I could, I don't know, I mean, I didn't assume that they are ordered in ascending order, but we could assume this. At least I draw it now like this, right? And then now, since this is true for every x, right? It's true. So let us just use a few x's, right? For example, d1 plus d2 half, right? Or something else in between here, and then in between to d2 and d3, something, etc., right? So you see, since the sign is non-negative here, and also here, right? So when you see that the alpha 2, for example, because it's non-negative here and also non-negative here, actually it's positive even, right? Because, yeah, I mean, if you choose, if a red point is not one of the di's, then this will never be 0, right? So, okay, so it's positive when you put in this x here, and it's positive if you put in this x here, right? And this means that alpha 2, for example, is certainly an even number. Otherwise, you would have a sign change between here and here, right? So, and in the same way, you deduce, like, for example, that alpha 1 is an even number by looking at this point and so on, right? Where, where this point, for example, is d1 minus 1, for example, right? Okay, so every alpha j is an even number, and of course C must also be positive, so it must be a square in R. And so I write now G, I define now G to be the square root of C. And when I take just this part here, take just one of these parts, let's say this one. And when I take here the alpha j half, so it's important that I take here half. And that makes sense because alpha j is an even number. Okay. So now we have f is g star g. So let's see why is this true? Why is f g star g? Okay, g star, what is g star? G star, so the square root of c is is an element from R. So the star does nothing to the square root of c. Well, here the star what does the star do here? It changes the I into a minus I. So it changes the the green thing into the yellow thing here, right? So I get here this yellow expression, right? And then here nothing is changed because all coefficients are in R here. Okay, so I get here red thing. To the power of alpha j half. Okay, so that's the g star. And the g star g, now if you multiply these two things, you see the square root of c times the square root of c gives c. This yellow thing times this green thing gives this product, of course. And this times these two red things multiplied give exactly that one. So we see f is g star g. Now, but g, of course, is a complex polynomial. I mean, it's a polynomial whose coefficients are in C. But I can write g as p plus iq, right? Because for every you know, all the elements from C look like this. So I can do this coefficient-wise. And then, yeah, so the real part of the coefficients, the polynomial whose coefficients are the respective real parts is called p, and the one with imaginary parts is called q, and then I have this, of course. And then this, and then I get here f is g star g, that means p, well, like g star is of course p minus iq, right? So p minus iq times p plus iq. Now, if you multiply this, you get p squared minus I times q squared. So that's actually plus q squared. And then the mixed thing here is ipq minus ipq is 0. Okay, very good. Now I want you to present a second theorem about univariate polynomials. In the theorem we just proved, the polynomial had coefficients from the real closed field, and I assumed that f is non-negative on the real closed field, and then I could show it's the sum of two squares over this real closed field. But one can ask now, what happens if f has a coefficient in a subfield of R, or yeah, let's say f has coefficients in an ordered field? Well, when this theorem might fail for several reasons, right? So, I mean, already if you have, so let's now say K is an ordered field, Kp is an ordered field, or K less than or equal is an ordered field, and you have a polynomial over k, and now you are asking when can I say that, when is it true that f is a sum of squares over that ordered field, right? Sum of squares, sorry, of polynomials, maybe, yeah, of polynomials. Over that ordered field, right? But in order for it to be such a sum of squares, well, already if f is a constant polynomial, right? The special case is that f is a constant polynomial. It's just an element from k, right? And when you see easily that if f is such as that, when the question actually is equivalent to being f being a sum of squares in k, right? Right, and that's easy to see, right? Okay, and well, you know that not every, there are ordered fields which have several, or there are fields that have several orders, right? Not only one order. And the intersection of all orders is on K is the sum of squares. You know that already, right? That's what we have proved. So if there are two orders on K, then not every non-negative element from K is a sum of squares, and therefore the condition that f is non-negative on K or on a real closed extension field of Kp, of K less than or equal, will certainly not be enough, right? Because already for constant polynomials it fails, right? So if you think about that, it seems quite reasonable that instead of that in this case one replaces this condition here by another condition saying that f is a sum of weighted squares where the weights are non-negative elements from K, from my ordered field K less than or equal. Right, so I guess I convinced you, or I hope I convinced you, that this makes a lot of sense to look at this condition here, right? And we don't clarify now when this is actually true. We will clarify it later. But yes, but we will. But you could also look here again at a similar condition like that f is a sum of weighted squares with non-negative weights of rational functions, right? You know, in Hilbert's 17th problem, I told you already, you need to take rational functions so that it's true. And so the question is, does it make a difference here of looking at rational functions or at these kind of representations? So weighted sums of squares of rational functions versus weighted sums of squares of polynomials. And turns out that in one variable, if I have just one variable, that is actually equivalent. And that's perhaps a bit surprising. It's not trivial. And the proof is due to Kessel's. I don't know if Kessel's looked actually at, if he looked at it in this general case, where you have here the weights. Perhaps he looked at the corresponding theorem without weights, or with all weights 1, right? But but the proof is the same. So it's due to castles. And this is the theorem. So let K with less than or equal be an ordered field. Suppose L is a non-negative integer. I have L polynomials over K in one variable, and these will be the numerators of rational functions actually, and the denominators will be the GI. So they should be non-zero because they will be denominators. And when I have the same number of weights, non-negative weights from K, and I take this weighted sum of these squares of these rational functions Fi over Gi, right? And I assume that this is a polynomial. Then I can write this polynomial. I mean, that's not automatic, right? That's an assumption. When I can actually write this polynomial, which is a sum of weighted squares of rational functions, as a sum of weighted squares of polynomials, and I can take exactly the same weights, and I take the same number of terms here in the sum. And so that's not trivial, and we have to prove this. And for this, we go to the next page. Okay. So without loss of generality, I can assume that each AI is bigger than 0, because otherwise those who are 0 obviously don't play any role here, right? And I can assume that all these with all these denominators Gi are the same, because I can just use a common denominator by multiplying the Fi's with suitable polynomials. And so it suffices to show the following. So let H be a polynomial for which there exists some polynomial G of degree greater than or equal 1, and F1 up to Fl polynomials satisfying Hg squared equals the sum of the AI Fi squared, right? And the idea is, of course, that in the first step, my G will be these GIs, which are all the same, right? And or except if G is if these GIs are of degree 0 already, and I don't have to do anything in any way. So, but otherwise, I take G in the first step to be my GIs, right? And H in the first step is of course this polynomial, right, which I have assumed to be a polynomial. And the Fi's and AI correspond really to these AI's and Fi's, right? And then what I do is, so the problem is somehow that this G has degree greater than or equal 1. If it had degree 0, I'm done. I already said this. So the idea is now to replace this G by a capital G, also non-zero, of course, by such that H capital G squared can also be written in that way, of course, with other Fi's, which I will call capital Fi. And the degree of capital G should be smaller than the degree of small g. And then I can iterate this, right? I can iterate this until I get to a degree 0 polynomial here. And then I'm done. Right, and my final capital Fi's are then VPI's. Okay, so when there is some G, so it suffices to show, let H be in this way, when there is some G with a degree that is smaller than that of G, and F1 up to Fl satisfying Hg squared is this. So that's to show. Maybe we should color it a bit. So that's now our hypothesis here, and what we have to show is the red thing here. And when we are done. So we prove this. So, and the idea, now I cannot explain really the idea behind this proof. It's ingenious. So the first idea roughly is that, you do a division with remainder. So you divide the fi's by the g. So that's the quotient, that's the qi, and that's the rest, right? The ri is the remainder, and qi, so division with remainder. The quotient is qi, and ri is the remainder. And the degree of remainder should, of course, be smaller than the degree of g, because I divide fi by g. Okay, and it might be 0, of course, when the zero polynomial has degree minus infinity. Right, so I mean this part, the part of fi which is divisible here by g, the idea is that this might hopefully make, not that you could turn this part already into some polynomial things, but it's not very clear, because when what remains is not what you want. But anyway, if the rest is 0 for all I, then we are really happy, right? When we set when we set g to be 1, the new denominator, and then fi to be qi for all I in 1 to L, and when we have hg squared equals h equals 1 over g squared. Hg squared is 1 over g squared times this, and so I have here it's this, and when I have that is this fi over g is qi, and that's fi squared, and then that's really what we want, right? So, but that was really the easy case. Now we come to a harder case. In the sequel, we suppose that there is an index I which makes some problems where the remainder is non-zero. Yeah, that will be, of course, the case that occurs usually. So, and I call the set of indices that make problems capital I. Now I set S to be this, and yes, and T, just accept it. T is this. Makes sense in any case, right? And the fi's are this, right? Where I use already the T and the S now. And the new G is a bit surprising, is actually SG minus 2D. Okay. Well, here it's maybe not yet surprising. Here it's just that nobody sees anything, right? Later we will see that capital G will be a quite surprising thing. Okay, when we obtain that hg squared is, okay, let's see, so that's, so I get 3 terms each time the h appears, and when I get s squared g squared, I square this term, right? if I square this term, I get 4t squared, it's here. And when the mixed thing here is minus 4 SGT, and when we h, you have always, right? So hg squared is this. And this is, hg squared was, of course, this thing, right? And so here I artificially introduce the term t here, right? And when I have to compensate for this, namely now I have minus 4st squared. Yeah, I've subtracted 4st squared, which I have to add again. I do this by putting artificially here an s, right? And otherwise this is the 4t squared h is here. Okay, so now this is, so I leave the first sum here unchanged here. And for the second sum, you know what is t plus gh? T plus gh is exactly this thing here, right? Okay, so I write that here. And s plus h is exactly this thing. Okay. And now this is, you know, I have now in each, I have everywhere with sum from I equal 1 to L, so I can put it on the outside here. And when I have everywhere the AI with weight, I can put it here. And when I get here a square, right, because this is s squared f, okay, let me maybe color it. I have here the s squared fi squared. And here the 4t squared qi squared, right? And then here the mixed term is minus 4, let me do it in green, minus 4s t, and then here we fiqi, right? And this gives me exactly this, what is this square here, right? And then sfi minus 2tqi, you see, that was exactly my fi, my capital Fi. So I have indeed hg squared is magically with sum here. So I have this condition, right? But of course, it's we have still to show that g is not a zero polynomial and that its degree is smaller than the degree of little g. Okay. So it remains to show that g is not a zero polynomial and the degree of capital G is strictly smaller than the degree of g. To this end we calculate, okay, let's see. So g is sg minus 2d. So g is therefore, okay, so we s is this yellow term here. And it's multiplied with g, so I get this term minus gh, right? So that is VSG, is up to here. And then I have here minus h. Okay, minus 2t, minus 2t. And that's just what I wrote here, right? So that's a minus 2t. And this is, so I can multiply this with g and divide here with g, so I have 1 over g, and then I have here g squared times this, minus g squared So yeah, if I minus gh plus 2gh, that gives gh, and this is multiplied with a g, so I have g squared h, and here minus 2g with sum here, which comes from here. And then this is 1 over g times g squared with, plus, now g squared h was with sum, right? And this I just write again here. And then I have that this is 1 over g times with sum. Okay, vi. So now I have everywhere again the sum over vi. So, and also the weight ai, it's everywhere. So I can take it out here. I can move it out. And then I have here g squared qi squared minus 2 g qi fi plus fi squared. And this gives me here g qi minus fi squared, of course, right? And this is 1 over g. So that was actually the remainder, the ith remainder, right? Of course. Yeah. So fi was g qi plus ri, right? So, and so I get here ri squared. So I get 1 over g times, and I don't need to look at those indices where the weight ai is 0, of course, so I can sum here only over the capital I. Okay, so why can g not be 0 now? If we had g equals 0, then this would mean that this sum would be 0, but the leading coefficient of this sum is positive for all the leading coefficients of the terms in this sum, which are polynomials over k, is positive, right, for all I and I, because it was ri was not a 0 polynomial, and the leading coefficient of this polynomial is ai times the leading coefficient of ri squared, which is clearly positive then. Yes, you know, in such a sum, the leading coefficients cannot cancel out. I mean, those coefficients of highest degree, so the monomials of highest degree that appear in any of these terms in the sum, they cannot cancel out, of course, right? They cannot, if I sum them up. So, I mean, the leading, let's say this way, the leading coefficient of this sum is a sum of the leading coefficients of these ai, of the leading coefficients of some of these ai or I squared. Maybe not all of them, but some of them. And then, yeah, this cannot be 0, because they are all positive in the ordered field k. So hence, g is non-zero. Okay, and what is slightly surprising is that our new g is actually this thing here, divided by the old g, right? So that's quite surprising, because you would perhaps think that the capital G is some kind of new version of small g, right? Yeah, but it's surprising that you define here something, and when you divide even by g, right? Okay. Because, so the old g times the new g is this thing, right? So because of the degree of Ri is smaller than the degree of g for all I, right? Because this was division with remainder. So we have that the degree of g is smaller than 2 times the degree of g, right? Because minus the degree of g, sorry, because the degree of this sum clearly is smaller than 2 times the degree of g, but when I divide by g, so I lose again this degree, right, so yes, and so you have g times capital G is the sum, so the degree of g plus the degree of capital G is the degree of the sum, right? And so and the degree of the sum is smaller than 2 times degree g, and so we have degree capital G is smaller than degree g, and we are done. Very ingenious proof, and we will use that later again. Okay, thank you very much for listening. So this was the subsection 2.1, the first subsection of chapter 2 in which we are now. And these were these lecture notes. And yeah, I hope to see you next time. Goodbye.